This is lesson 5, focusing on the properties of linear relations in the functions and relations unit. So let's start off with defining this term, linear relation. This is something you've probably seen in your courses before. So a linear relation is a special type of relation where the x and y values increase or decrease by a consistent rate. So the x and y values, I'll say change, because they could be increasing or decreasing at a consistent rate. And we'll see examples of what we mean by that. Consistent rate. When we look on a graph, the points, because they're increasing or decreasing by a consistent amount, they're going to line up in a straight line. One way to remember the definition of a linear relation is it actually has the word line in it, right? And we say here that the points are lining up in a straight line. Okay, let's look at a simple example to start. We have a relationship here that's represented as both a graph and a table. We have number of toppings, that is our independent variable, and that's shown on the x-axis of the graph, and then we have the cost of a pizza shown on the y-axis. So what patterns do we see in the table? So let's look at the table and what's happening to the values. So I can see that the number of toppings is going up by 1 as I progress down the table. And the cost, if I subtract those values, $10.75 minus $10 is 75 cents. And that pattern stays consistent. So every time we increase the toppings by 1, the cost is going up by 75 cents. This is what we meant by consistent increase before when we were defining what a linear relation is. Okay, so we can say here x values, or the number of toppings, is increasing by 1. The cost increases by 75 cents. Okay, describe the pattern that relates the cost of the pizza to the number of toppings. So basically, if you have a pizza with no toppings at all, it's going to cost you there's going to be a base cost of $10. And then every time you buy new or however many toppings you want, those are each going to cost you an additional 75 cents. So we can say something like this, like the base cost of a pizza is $10 for a pizza plus 75 cents per topping. We could make an equation. We could make it something like this. The cost of the pizza is $10 plus 75 cents times the number of toppings. We could also write that in function notation like this. C of n equals 10 plus 0.75 times n. So here we're using n for the number of toppings. You could also use t for toppings, and then we're using c to represent the cost. Okay, how can you tell from the table that the relation is linear? So specifically talking about the table, the increases are consistent. And then from a graph, the points are in a straight line. Not every relationship is linear, but there's lots of real-life examples that produce a linear relationship. The points are in a straight line. All right, let's look at some more examples here. Here we have some graphs. These ones here, So we're supposed to pick out the linear graphs. Linear, again, it has line in the word. We're looking for points that line up in a straight line. This is not linear, and this is not linear. These points are not in a straight line. It's easier to see too if you connect them. We can see there's no consistent pattern there. But these ones are in a straight line. Are these all also functions? Yes, they all are functions. They pass that vertical line test. Each x value only has one y value for every example there. So I can say each x value is associated, I'm going to associated with one y value in each graph. All right, let's look at another example here. It says, which table represents a linear relation? It's a little bit harder because you can't just like look at the table and it's not. We have to look at the differences or the pattern to see if it's consistent or not. So let's look at the first one here. It looks like we have temperature in Celsius and then temperature in Fahrenheit. Let's look at the increases in the x values. Looks like these are all going up by 5. So far it looks pretty good, but we have to make sure the y values are also increasing consistently. And here looks like there's a consistent increase of 9. So every time the Celsius temperature goes up by 5, the temperature in Fahrenheit goes up by 9. So this one is a linear relation. Let's look at this one. This is current in amps and then power in watts. So here we have a nice consistent increase by 5 again. But over here, let's see. So from 0 to 75, that's an increase of 75. From 75 to 300, if I subtract those values, I get a difference. 300 minus 75 equals 225. That is not a consistent increase. And then here again, I get another difference. It's plus 375. And then here, it's different again. So because the consistency, there's no consistent increase, it's not the same amount every time. I'm going to erase some of this annotation here just to make it a little more clear. This one is not a linear relation. So both the x and the y values have to be increasing consistently at a consistent rate. They don't have to be the same consistency, but it has to be consistent in order to be linear. All right, let's go here to the next page here. We're going to look at rate of change. Rate of change measures how, like, the relationship between how the y values are changing compared to the x values. And another really common word for rate of change is slope. So when we're looking on a graph, it's actually the steepness of the line. So the larger the slope, the more steep the line appears. So the rate of change describes how much the y value change per unit change in the x value. So there's a couple of different ways to calculate the rate of change. So you can just use this change in y over change in x. Sometimes you'll see this symbol. This symbol means change in. It's like a short way to write it. It's the Greek letter delta. So you can use that for short. Another way to write this same equation, when you're finding the change in the y value, what it's going up by or going down by, what you want to do is subtract two y values. So you can also write this y2 minus y1, so you subtract two y values and then you subtract two x values. Okay, so those are different ways to calculate the rate of change. Sometimes another one I'm going to write down here you might hear, especially when you're looking at a graph, is rise. That's how much the y values are changing over the run. But we'll see that more in graphs, and we're going to focus on tables here. All right. So I'm going to use blue for my change in y, and then yellow for my change in x. All right, let's look at this next one here. So we have time as our independent variable, and then distance from home as our dependent variable. Let's look at the patterns. Looks like every time we move down a row in the table, the time is going up by 2. And looks like my distance from home is actually decreasing. If I subtract these numbers, I get negative 125. Negative 125. It's going down by 125. So that's the change in the y value, and 2 is the change in the x value. So as time increases, it's going up. We're just going to describe the pattern first. By 2 hours, the distance from home decreases because it's going down by 125 meters. Okay, so let's put that into our equation now. The rate of change is equal to the change in the y value over the change in the x value. So what we found here was that, oops, I'm using the wrong color, sorry. The change in the x value was 2 hours, and the change in the y value was negative 125 meters. And we want to use units if there is a measurement associated with it. So we want to go down by 125 meters every time we go up by 2 hours. And you can divide those numbers. Remember, a fraction is just a division. And so we would get, I'll just start it on a new line actually. That looks neater. 125 divided by 2 is negative 62.5. And the units are going to be the same as the units I see here. Meters per hour, meters over hour, or meters per hour. You could write it like that. There we go. Okay, let's look at the next one. Maybe you could pause the video here and try the next two on your own if you feel comfortable, or you can do them here with me. So we have time in minutes again, and then volume of water in liters. So again, let's look for the patterns. Looks like this time the time is going up by half a minute, 0.5 minutes. And the water is, again, decreasing here. If you subtract these two values, 6.3 minus 5.9, you get a difference of 0.4. So looks like every time, let's fill in these words, as time increases by 0.5 minutes, the volume of water decreases by 0.4 liters. So slope is a measurement of how these changes relate to each other. So the change in the y value is negative 0.4 liters. The change in the x value is 0.5. So let's put these numbers in. We have to put units. And if I divide those values, I'll get just one number, which is negative 0.8, and I want to use the exact same units I see here. I have liters over minutes, so it's liters per minute. So that means the volume of water is going down, that's what the negative sign represents, by 0.8 liters every minute that passes. Okay, let's go do the last one. We have this, again, pause the video, try this on your own if you would like. I'm going to go a little faster here. So now you see the number of people is going up by 5. That's consistent throughout the whole table. Here, you might want to, so to see that what the difference is, sometimes if the numbers are big or if there's decimal places, you can just subtract. But we can see here that the values are going up by $45 every time. So as the number of people increases by 5 people, the total cost of food also increases this time by $45. Okay, so change in y over change in x is going to be $45. Goes on top, that's the y value, right? That goes here. And then 5 people. You can divide those numbers to get one answer, $9 per person. We don't say people anymore because it's only talking about one person. So the cost is going to go up by $9 a person. Okay, that's rate of change. So that describes how the pattern of x and y changes relate to each other. All right, that's the end of the lesson.